I want to thank the organizer for this wonderful winter school. I mean, I learned a lot about non-fermi liquid states. So I will talk about SYK and non-fermi liquid states. Actually, the purpose is to construct some non-fermi liquid state based on SYK kind of physics, not necessarily the SYK model, but SYK physics. So let me first introduce my collaborators. Most importantly, Xiaochuan Wu actually is in the audience. So actually, he did a lot of calculations. So actually, if you have a hard question, you know who to ask. And so Chao Ming was a postdoc in KIDP and also Station Q, and now he's a Cornell faculty, and also have many other faculties. Many other collaborators collaborate on the related subject in the past few years. Yeah. So actually, the previous talks have introduced a lot about fermi liquid and non-fermi liquid. So I will just give a brief reminding of all the basic concepts. Like the fermi liquid, basically, it's a fermion system with actually a sharp definition of the Fermi surface. And actually, most importantly, in the fermion Green's function, the self-energy will be dominated by the non-interacting term, which means that the imaginary part of the fermion self-energy, which is the decay rate, actually is much smaller than the energy of the quasi-particle close to the Fermi surface. So that means that when we get closer and closer to the Fermi surface, actually the fermion excitation, or actually if the system has a charge then we can say the charge 1 excitation of the system behaves more and more like a non-interacting fermion with a renormalized mass. Also, the IR fixed point, the infrared fixed point of the Fermi liquid, the original Landau theory of the Fermi liquid actually has a lot of conserved quantities. So basically, actually, the fermion number at every patch of the Fermi surface is actually conserved. So that's actually a system with a lot of conserved quantities and with a lot of, you can say with a lot of symmetry, emergent symmetries in the low energy limit. And actually has a, phenomenologically has a pretty famous scaling law. The resistivity will scale with temperature to the power 2. So actually, the most I think the best way to describe or justify the Fermi liquid is the Shankar-RG procedure. So if we just start with a Hamiltonian with actually just a momentum conserving scattering. That's a lot of choice of the scattering process, but actually Shankar showed that under RG process, under renormalization group, in the infrared limit, actually only a few processes will survive under RG in the infrared limit. So 1 and 2, omega 1, omega 2 are the incoming momentum as the Fermi patch on the Fermi surface. And actually turns out, so 1 and 2 will interact and scatter into 3 and 4, But so what Shankar showed is that under RG, it turns out that, at least in 2 dimensions, this is especially simple. In 2 dimensions, turns out that 1, 2 actually will just scatter into 3, 4, and 3 equals to 1, and 2 equals to 4, or the other way around. So it means that actually basically these 2 electrons either just keep their own momentum and keep going, forward scattering, or they just exchange their momentum, or they just exchange their momentum. So this is why, actually, I said before that the fermion number at every patch of the Fermi surface is a conserved number in the infrared limit. But actually, there's another interaction which actually is 1 and 2, actually they are opposite from each other, and they scatter into another pair of opposite momentum. So it turns out this is the BCS scattering. So actually, depending on the sign of this scattering, suppose it's an attractive interaction, then under RG, this attractive interaction will be marginally relevant. Will be marginally relevant. So this marginally relevance means that the Fermi liquid or the Fermi surface is actually unstable against the attractive interaction with this process. And actually, the Fermi surface is actually unstable against forming a superconductivity. So it turns out the superconductor, the BCS, so this process will become very relevant and non-perturbative at exponentially suppressed low energy scale. So we are going to have a superconductor, BCS superconductor, at a very low energy scale. So this also means that we can view Fermi liquid with a Fermi surface. We can view Fermi liquid with a Fermi surface as a parent state of the ordinary BCS superconductor. So this is some very brief review of the Fermi liquid. So now non-Fermi liquid, basically non-Fermi liquid just means anything which is not Fermi liquid, but still metal. So basically it has no well-defined Fermi surface, and actually fermions are never non-interacting, even at what we think would be the Fermi surface. And actually, experimentally, the non-Fermi liquid seems to be the parent state of many superconductors. So for example, this is a very typical schematic phase diagram of a non-Fermi liquid. So there's some kind of ordered phase. There's a Fermi liquid metal, and there's a control parameter. And this region is the quantum critical region with a non-Fermi liquid behavior. There's no quasi-particle, but then at low temperature, usually the non-Fermi liquid state at a very low temperature is actually preempted by a superconducting phase. Okay, so it means that experimentally, at least this suggests a non-Fermi liquid state actually is usually a parent state of some kind of superconductor. Okay, of some kind of superconductor. So yesterday we heard some very nice introduction of non-Fermi liquid. Actually, one more traditional way of getting non-Fermi liquid is to start with a Fermi liquid state, start with a non-interacting limit, and we couple the fermions. We couple the fermions with some other particles. For example, we couple the fermions with the quantum critical modes. Then actually the quantum critical mode may actually interact with the fermion very strongly. So yesterday we heard that the interaction can be relevant. And when the interaction is very relevant, it's going to kill the quasi-particle. The decay rate of the fermion can be very, very big. So it means that the fermion will no longer have a long-lived quasi-particle. Okay, so that's how we get a non-Fermi liquid. Okay, so the quasi-particle will become short-lived. Okay, so this actually is a very fun problem. And yesterday we heard there's a lot of method or tricks developed for this formalism. So for example, this was like a two-patch or one-patch theory. And actually, by power counting, we can actually show that this boson fermion coupling is actually relevant. And actually, there's many efforts have been developed to seek for a controlled expansion of this relevant coupling constant, and this relevant coupling constant may flow to a fixed point, which is a non-Fermi liquid fixed point. And yesterday we heard that we can actually make the boson dispersion relation to be a non-analytic dispersion relation and do an epsilon expansion, or we can just do a dimensional expansion, finding the upper critical dimension is 5½ and do epsilon equals to upper critical dimension minus actual dimension expansion. Okay, there are many other relevant. And tomorrow, actually, I'm going to talk about some perturbative method, starting from the more traditional approach, like this one. But today, let me actually try to talk about a new perspective of constructing non-Fermi liquid. Okay, which just started a few years ago. So as I said, the previous efforts was to start with a Fermi liquid and try to make it a non-Fermi liquid. Okay, so this is like a standard method of studying interacting conformal field theory. So the standard method of studying interacting conformal field theory is to start with a non-interacting or Gaussian theory and start doing perturbation around it. Okay, so for example, if you want to study the three-dimensional Wilson-Fisher kind of a phase transition, we start with a four-dimensional theory, which is the upper critical dimension, and we just assume that a dimension is not so far away from the upper critical dimension, then we do perturbation around that. So we just get a fixed point, which actually is not so far away from the non-interacting fixed point. Okay, but actually, so those fixed points are perturbative fixed points. So actually, another approach is that is there going to be a exact soluble model for a generic non-Fermi liquid state without doing perturbation, starting from a Fermi liquid state? Okay, so is there such a model? It's like solving like a 1+1 dimension or 2-dimensional conformal field theory. We know that the 2-dimensional conformal field theory is actually a very big topic, and actually most of them cannot be very well approximated from a non-interacting conformal field theory. So we need some so we need some other algebraic or other method to study this this theory. I mean, actually, some of them are exactly soluble. Okay, so actually, SYK model and SYK type of models. Okay, they fall precisely into this category. There are different versions of the SYK kind of model. Like the first version actually was not. I mean, okay, so I will talk about the version later. But actually, I want to say that there's a very nice review And also introduction in this paper, it's a very long paper, has all the detailed calculations, okay? Yeah, and this SYK model has many, many desirable features, many amazing features, okay? So besides being exactly soluble with a non-fermi liquid solution in certain theoretical limit, of course, it also has, low energy bosonic modes of this system also has a holographic dual, and it's also maximally chaotic, which means that something called a Lyapunov exponent, which describes how strong the chaos is, actually reaches the bound. So it means the maximally chaotic. So, but for the purpose of this talk, I will just try to focus on the first feature. Okay, SYK is a very big subject, so I cannot really review everything. So let me just focus on the first feature of this model. So what does this model look like? Okay, so the theoretically simplest version of this model turns out to be actually looks most unrealistic one. For example, this is the theoretically simplest version of the SYK model. It's actually a large n number of fermions, a lot of fermions, and a lot of Majorana fermions, and they all interact with each other. They have all-to-all interaction. Okay, so a very non-local all-to-all interaction. And this J, the coupling constant J, actually is random, is purely random, and actually obeys a Gaussian distribution. Okay, obeys a Gaussian distribution. So this actually is not the first version. It's not the first version of the SYK model. The first version of the SYK model actually was written down by Sachdev-Ye-Kitaev in 1993. So it turns out that their version of the model actually does not have an all-to-all Fermi interaction. It's actually more like two fermions are on the same side, the other two fermions on the different side. So it's like a quasi-local kind of interaction. So it's a local bilinear interact with another local bilinear, okay? But actually the solution is pretty much the same. The solution is pretty much the same. Okay, so the most important feature of this model is that suppose I just want to solve this interacting model in the most standard way, which means that suppose I want to sum over all the Feynman diagram. Okay, if I want to sum over all the Feynman diagram, so it turns out one thing we can note is that actually in the large n limit, we don't have any planar diagram issue. Okay, we don't have a sum over infinite number of diagrams. So it turns out that in the large n limit, only the wave function renormalization is the leading order in large n. Okay, so all of the vertex corrections actually are subleading in the large n. So that means that actually there's a very nice Schwinger-Dyson equation that we can use self-consistently to sum over all the diagram. Okay, so so it means that the Green's function is related to the self-energy, and the self-energy has an exact relation with the Green's function. Okay, so this kind of self-consistent Schwinger-Dyson equation. So this actually is a pretty simple equation to solve. Okay, pretty simple self-consistent equation to solve. Normally the Schwinger-Dyson equation will also have a vertex correction, but as I said, the vertex correction is actually not going to be here because in the larger limit, the vertex correction is completely suppressed. Okay. And also, because the vertex correction is completely suppressed, turns out that based on the looking of this Hamiltonian, you can pretty much guess what the solution is going to be. Okay, what the solution is going to be. So basically, in the 0 plus 1 dimensional field theory, a Majorana fermion will have scaling dimension 0 as the non-intact limit, the chi partial T chi. Okay, then actually when this interaction becomes relevant, it will want this whole term to have scaling dimension 1. And because there's no vertex correction, it means that every fermion will have scaling dimension 1/4. Okay, the solution will give you every fermion have scaling dimension 1/4. So it turns out that that's exactly the solution. Okay, that's precisely what the solution looks like. Okay, so if we solve the Schwinger-Dyson equation, it turns out that so this is the free fermion. Okay, free fermion Green's function in the 0 plus 1 dimension. You can see there's no decay. Okay, there's no decay, so it means that the free fermion has scaling dimension 0. And this is the free fermion Green's function in the frequency space. And then by summing over this Schwinger-Dyson equation exactly, you can see that the disorder average, okay, the disorder average fermion Green's function will be 1/tau to the power 1/2, which means that actually the scaling dimension of fermion is actually 1/4. Okay, this is actually consistent with a very naive power counting of the fermion. Okay, fermion will have scaling dimension 1/4. And in the frequency space, it actually looks like this. Okay, so it's actually a very simple solution. But immediately you recognize that this is a non-Fermi liquid. Okay, because of a Fermi liquid, the Green's function will be I omega. Okay, the leading term. But in the solution of this guy, the self-energy will dominate these I omega terms. Okay, so the solution of the SYK model is a non-fermi liquid already. Okay, so that solution is a non-fermi liquid.
So this is only at the particle hole symmetry.
Sorry?
This is only at particle hole symmetry.
For random fermi, there is automatically a particle hole symmetry. But actually, for complex fermi, the solution is slightly more complicated. But actually, scaling dimension is the same. Yeah, scaling dimension is the same. Yeah.
But I also know if you change like the statistics of J, right, then the scaling dimension.
Oh yeah, that's right. Yeah. So
that'll contradict the naive count of the power.
oh, then that some vortex correction will play a role. Actually, I will get to that in my next example. Actually, sorry. So if you change the statistics, some of the other diagram will also come in.
Yeah.
Some other diagram will also come in. Yeah. So I will get to that in my next example.
Just directly look at this interaction.
Yeah. Right. I know. So my assumption is that there's no vortex correction. So it means that all the scaling will just be distributed evenly into all the single operators. Yeah. Well, okay. So how do we deal with SYK model? So besides summing over the Schwinger-Dyson kind of equation, another very useful approach is by bosonize it. Okay, it means that we just try to integrate out the fermion, introduce the fermion-Green's function and the self-energy as the fermion bilinear. So everything is actually going to be a bosonic field in this effective action. So this is called a G sigma action, and actually, so it turns out that you can also show that in the large N limit, the saddle point for this G sigma action is also exact. Okay, it's also exact. So this kind of G sigma action is actually very useful. So the banana is for me, or? Yeah, so this G sigma action is actually particularly useful if we want to study some thermodynamic properties. Okay, study the thermodynamic properties of, for example, entropy and many other things, and also some reparameterization mode of the system. And also very useful to do a one-van effect calculation. Okay, suppose we want to study what happens if you have a finite number degree, then this action is going to be very helpful for this purpose.
What's the difference between SYK4 and the original SYK?
Oh, yeah. So as I said, I mean, so also, right? Okay. So SYK4 means that these four fermions, they are all at different locations. The original SY model without a K is actually these two fermions are at the same location. These two fermions are at the same location. But I mean, it's basically a spin model. It's a spin-spin interaction. But actually, it's Subir wrote a spin in terms of fermion bilinear. So two fermions will be at the same location. The other two fermions at a different location. It's still long-range random interaction. Yeah, but it's not as non-local as this one. That needs to draw some diagram. Sorry, I mean, I'd rather not do it right now because actually it takes time. But actually, you can the vortex correction is like the calculating the OTOC, the output time correlation function. Actually, so those correct you can show those diagrams actually are subleading one of them. Yeah, but yeah, I'd rather not do it right now. Anyway, so. Okay, so as I said, the SYK model, its exact solution is actually a non-fermi liquid state. Okay, so so the first question we try to ask is that, okay, this is a non-fermi liquid state. Okay, can this non-fermi liquid state be a parent state of a superconductor? Okay, so that's a question that actually we try to ask. Okay, so it turns out that, okay, so this means that we start from the SYK kind of model. We perturb it with some other interaction. I mean, this is a Toyen model, but actually we can just add some other, any kind of interaction basically. So this Toyen model we tried is that this is a four-Fermi interaction, which actually is a Gaussian distributed random interaction. So the first model we tried is to turn on a four-Fermi interaction, but now the coefficient is Cij is a Gaussian distributed random interaction, and the CKL is another Gaussian distributed random interaction. But actually, they follow the same randomness. Okay, they follow the same randomness. So actually, if we look at this term, the product of two Gaussian distribution, variable is no longer Gaussian anymore. So it means that this actually can be viewed as a non-Gaussian full-Fermi interaction, okay, even non-Gaussian full-Fermi interaction. So it turns out we try to solve this system, okay, we try to solve this model. So what we do is that we can obviously see that this can be viewed as a square of a Fermion bilinear operator, so we can just write it as a, introduce a Hubbard-Schnodvig field, boson field B, and to see that whether we can find a phase where B has a non-zero expression value, okay, where B has a non-zero expression value. So if B condense, it's like we condense a fermion bilinear operator, so it's going to be the analog of the superconductor. Okay, it's going to be an analog of the superconductor. Okay, so actually, so normally the superconductor Cooper pair will break the charge U1 conservation of the fermion system. Here, because I mean this toy model has a Majorana fermion, so it means that there's no fermion conservation, but actually there's still time inversal symmetry. So it means that actually this pairing, this B operator will be odd under time inversal. So this means that when B condense, it spontaneously breaks some symmetry, okay, and it's analog of the superconductor. So it turns out that indeed we can, we can show that by solving this G sigma kind of action, we can show that at exponentially low energy scale, okay, exponentially low energy scale, indeed, this SYK model is unstable against the superconductor, okay, it's unstable against superconductivity. 1 second. So this means that the SYK non-Fermi liquid, just like the Fermi liquid, the SYK non-Fermi liquid is also a parent state of a superconductor. It's also a parent state of superconductor. Okay, question?
What symmetry does this superconducting state break?
It breaks time inversal. Yeah, because actually, so here I define time inversal as the edge state time inversal of the Kitaev chain. So you just time inversal, just take I to minus I, but it keeps chi invariant, keeps the Majorana fermion invariant. So actually means that any fermion bilinear Hermitian operator is time inversal odd. So actually, so the Cooper pair.
It's also possible to construct a complex fermion.
Exactly, complex fermion is completely possible. I don't know why I didn't do that actually. Sorry. Yeah, the first model we tried just the Majorana, but actually, if you just start with the complex fermion version plus some complex fermion interaction, you will get exactly the same result. Yeah, so I don't know why we didn't do that. Yeah, right. Yeah. Anyway, so another thing to do, which is actually is very much like the Shankar RG, very much like the Shankar RG, is to do a one loop RG calculation for the U. Okay, one loop RG calculation for the U. It's actually the same kind of bubble diagram as Shankar did. Okay, as Shankar did. Basically, since we know the exact correlation function of the fermion, so we can calculate the larger limit one loop RG exactly. Okay, so actually, so we compare our mean field calculation and also the RG prediction of the critical temperature. So actually, they match actually very well. Okay, they match very well. Especially at weak coupling. Okay, they match very well. Okay, and this J4 is the interaction strength or the Gaussian average strength of this 4 Fermi interaction, and this J is the Gaussian average interaction of this C interaction. Okay, of C. So this actually takes a very similar form as the BCS theory. Okay, it takes a very similar form as BCS theory.
The original SYK4 isn't fermion you want to charge already not?
Say again.
The original SYK4 isn't the fermion.
Yeah, I know. Yeah, but this SYK4 has time inversal symmetry. I'm saying that in my Majorana fermion of the story, actually the superconductor is viewed as a time inversal symmetry breaking phase. It breaks some symmetry, but as I said, if I replace it by C dagger, CC, and this is another C dagger, CC interaction, actually we will get a phase where the charge U1 symmetry is spontaneously broken. It follows the same calculation, exactly the same calculation. Yeah, follows the same calculation. Yeah. Oh yeah. So now I remember why we didn't do that, because actually the original motivation was actually not to find a superconductor, but to find chaos to non-chaos phase transition. Okay, because actually the SYK model, as I said before, SYK4 model is a maximally chaotic, but the SYK2 model, because of the free fermion, has no chaos at all. So basically, what we want to find was to find a phase transition. To find a instability of the maximally chaotic model towards a non-chaotic model. So it turns out it's true, because actually we can show that so what we just said is that at a very low temperature, the B operator, which is a Fermat bilinear condense. And when Fermat bilinear condense, this model reduced to a Fermat bilinear models. And the Fermat bilinear model has no maximal chaos. Okay, so it means that this superconductor transition can also be viewed as a chaos to non-chaos phase transition. Okay, chaos to non-chaos phase transition. Yeah, right. Okay. Also, actually, another thing we tried is that using this kind of model, we can also build a thermal metal to a thermal insulator, thermal metal to insulator phase transition. Okay, so actually, there are many works which try to connect the SYK cluster into a lattice. Okay, so for example, the first attempt was actually made by a Stanford group. So they try to make so every cluster is a SYK4 model, and they try to connect them. They try to connect them using the SYK4 kind of interaction. So every island is a SYK4 model, and also between different islands there's also a SYK4 kind of SYK4 kind of interaction. So this term, the first term plus the third term, will give you a thermal metal. Okay, we'll give you a thermal metal. You'll calculate thermal conductivity and everything, become a thermal metal. But now suppose I turn on the term which I had before on every island. Okay, if I turn on this term I had before on every island, so it turns out that below certain temperature I can show that this term will cause some spontaneous symmetry breaking. Okay, will cause some spontaneous symmetry breaking. And when it causes spontaneous symmetry breaking on every island, it will spontaneously generate a SYK2 model. Okay, so you got SYK2 model. So when every island is SYK2 model, then between different islands, the full fermion tunneling is going to be irrelevant. Okay, it's going to be irrelevant. So it means that when every island is dominated by a spontaneously generated two Fermat interaction, then the inter-island hopping is irrelevant, and the system actually will become an insulator. So that means that in this one-dimensional chain constructed with the SYK model, there's a very natural thermal metal to insulator phase transition. Okay, thermal metal to insulator phase transition. Question? There's a thermal transport, right? Only thermal transport. Yeah, there's no charge transport. Yeah, in this system.
Can be also viewed as the MBL?
Yeah, precisely. Yeah, right. You can also view MBL transition. Yeah. Yeah, but right. I mean, yeah, maybe also MBL transition, but actually on every side, so eventually we have a free Fermat term. So actually, I'd rather not use the MBL kind of words, but and also.
Space that's intersite.
Yeah. No. I mean, another thing. Another reason I try to avoid using MBL is that MBL means the whole spectrum is localized. But here we only calculate the ground state. Yeah, only calculate ground state. So actually, I'd rather say just the thermal metal to insulator transition instead of MBL transition.
You're generating bilinear terms, but you're not generating intersite.
No. That term is forbidden by some gauge symmetry in this system. That's more detailed. But actually, I can guarantee that's not generated. Yeah. Okay. Question? Okay.
So can you do the same thing with complex fermions?
Yeah, we can. Yeah, definitely. Sorry?
You can obtain a metal insulator?
Yes, definitely. Right. Yeah.
By the same mechanism?
By the same mechanism. Yeah. It's by very similar mechanism. I believe we can generate that.
What about two dimensions?
I have to think about that. I have to think about that. But actually, I wouldn't say it's that difficult, because actually a lot of all the SYK kind of calculation, basically they are reduced to calculation on every site. So it's very dimensionally insensitive. Yeah, right. So maybe it can work, but I'd rather not promise right now. I can think about that. Yeah, but this is a two-dimensional model. Okay, although the motivation is very different, but this is so what I will get to is a two-dimensional question.
In the previous slide, when you connect these SYK models,
Yeah.
what is the dimension of each of these? Can I call it side?
Yeah, you can call this a side or island.
Or island?
Yeah.
What is the dimension?
Sorry, take it.
What is the dimension of the Hilbert space?
Oh, this is 0, or with a lot of degree freedom. Yeah, because actually everything is interacting with everything, so I would call this a zero-dimensional system. But it's Hilbert space is in the large n limit will be infinite, right? In the large n limit will be infinite. For finite n, it's certainly finite, but actually we have to calculate 1 of n correction, to see what the solution is. Okay, so actually the part of the reason SYK model becomes interesting to condensed matter physics is because people realize that actually using SYK model actually is quite natural to construct a strange metal. Okay, very convenient to construct. Actually, it's very simple to construct a strange metal. So this actually is the first work made this attempt. So the idea is similar to what I had before. So basically, so they connect different cluster together. So every cluster is a SYK4 model, but it's a complex form SYK4 model like this one. And then they turn on a random tunneling. Okay, they turn on a random tunneling between different islands. Actually, this doesn't have to be random at all. So they turn on a random tunneling between different islands. Okay. So then they calculate the conductivity on the lattice. Calculate the conductivity on the lattice in the lattice scale. The calculation is complex, but actually the result can be very naturally interpreted. Okay. So for example, we know that as I emphasized many times before, the key of the solution of the SYK model is that every fermion has scaling dimension 1/4. Okay, of the scaling dimension, of the scaling of time. Scaling of time is scaling dimension 1/4. Then the current operator, okay, the current operator, which can be which can be derived from this tunneling term. The current operator is a fermion bilinear. It has scaling dimension 1/2. Okay, and then actually it turns out that the conductivity is just current correlation. Okay, divided by frequency. So based on this, just by power counting, you will see that eventually the DC conductivity will scale with the temperature linearly. Okay, it will scale with temperature linearly. If you start with the SYK solution and just do power counting, do very simple power counting, you will expect the resistivity to scale linearly with temperature. Okay, but this result actually this result uses the solution of the SYK physics. Okay, but we know that with this term, with this t term, it's a little hopping t term. Of course, the SYK solution will break down at a very low temperature. So this means that this linear T resistivity, okay, this linear T resistivity only applies to a finite energy window, for a finite temperature window. And specifically, in this paper, they show that it actually applies to the energy window below U, which is the energy scale of the full Fermi interaction, above T squared over U. Okay, T squared over U. Okay, within this temperature window, we are supposed to see a linear T resistivity. Okay, we are supposed to see a linear T resistivity. As I said, the calculation can be complicated, but actually the reason for the linear T is very simple. It's just that every C has scaling dimension 1/4.
What happens for temperatures below T squared over U?
Oh yeah, then it actually becomes some other power. I forgot what power it is, but it's definitely not going to be. So for example, suppose the T is not random, right? Suppose T is not random, then when at very low temperature, the T will give you a Fermi surface. So actually it becomes a random Hubbard model, something like that, right? So whatever scaling that is will apply, right? So the key point is that actually suppose U is much larger than T, then there's a very large energy window where there's a linear T resistivity. It's actually very natural to expect that.
But the p-factor, so if I would connect it into 1 over tau, the p-factor isn't going to be...
The prefactor is awkward because the prefactor is going to be proportional to this T, a T over U actually. So it means the prefactor is not going to be order 1. Yeah.
Much smaller.
The conductivity has a coefficient much smaller one, which means resistivity is actually large.
Oh,
yeah.
Yeah,
It's not a way around. Yeah. So yeah,
so
right.
Super Planckian.
Yeah, right. It's something like that. So yeah, that's the point which I was about to make. So but actually early this year there was a work by Sobir. Actually, they tried to get a Planckian kind of metal. Using this kind of physics. Okay, so ever since then, actually, there has been a plethora of works. Okay, trying to explore what kind of other models we can actually build to give us a strange metal kind of physics. So this is a effort made by Harvard and also MIT group. So actually, so they have two orbitals of fermions. Actually, they view this F as a slave particle of a local moment, and as you see is some itinerant fermion. So actually, they also have like a random SYK kind of physics between F and C, and also within F itself. So new feature they try to put in the model is that now This J, or those J and G, they are random on every site, but actually every site are supposed to have like correlated the same randomness. Okay, so it means that for every random choice, actually there's a translation invariant. So actually there's a moment in space which you can build in this model. Okay, this moment in space which you can build in this model. But actually the solution turns out to be similar to the previous case. Okay, so we can ask the natural question, because actually the fully random Gaussian interaction with a zero mean, of course, actually is kind of very unnatural. So the question we can ask is that can we bring this kind of SYK constructed non-fermi liquid state step by step closer to reality? Okay, we can ask this question, whether we can bring them step by step closer to the reality. The first step that we can think of is that can we remove the fully randomness? Okay, can we remove the fully randomness of the SYK model? So it turns out actually this can be done. Okay, this can be done. So for example, this actually was a series of a model developed by string theorists. So it turns out that suppose we start with a non-random, okay, start with a non-random, still 0 plus 1 dimensional model, okay, non-random, 0 plus 1 dimensional model, interacting fermion model, but now the fermion will carry 3 index, okay, we'll have a 3 index, and this index will contract in certain way, okay, will contract in certain way. I mean, you can stare at it and figure out how they contract, but I'm saying that when they contract in certain way, you can show that actually the same kind of diagrammatic tricks for the SYK model will work here. Okay, work here. I mean, this actually is quite amazing in the sense that if every fermion only carry 2 index, we know there's a famous planar diagram problem. Okay, this model becomes insoluble because we have to sum over infinite number of planar diagrams. But turns out that for 3 index, we only have to sum over a finite set of diagrams. Okay, so turns out that also the vertex correction still going to be suppressed in the large n limit. But then with the finite n, turns out that with the large n limit, turns out that this model we also only need to sum over the self-energy correction, and also there's a very well, very nicely looking Schwinger-Dyson equation that we can solve. The solution will be the same. Okay, solution will be the same as the SYK model, but now we don't need fully randomness. Okay, so another question we can ask is that can we go beyond the linear T resistivity? Okay, so for example, we know that actually in reality, actually non-fermi liquid means that pretty much anything the resistivity scale with temperature with the power smaller than 2. Okay, smaller than 2. So and in reality, indeed, actually the power can be anything. Of course, that could be crossover, but actually. In reality, the rho can scale with T with pretty much any power. Okay, with pretty much any power between 1 and 2. Okay, so the question is that can we actually construct? Okay, can we actually construct a series of exactly soluble or actually a pretty controlled limit of the based on the SYK physics? First of all, we don't have the randomness. Okay, we have like we have a non-random interaction, and second, we have a tunable. Okay, we have a tunable scaling of the transport. Okay, we have tunable scaling of transport. So it means that transport coefficient alpha, rho as a t to the power alpha, the alpha can be tuned between 1 and 2. Okay, between 1 and 2. So it can be tuned anywhere between the marginal fermi liquid and also fermi liquid. Okay, can be tuned anywhere between these two. Okay, and also it has better. That alpha can be tuned by the charge density. Okay, it's going to be better if the alpha can be tuned by charge density, which is often the case in reality. Okay, so one natural thing to expect is that we know that the reason the original SYK model can very naturally give us the linear T resistivity is because every fermion has scaling dimension 1/4. Okay, so now it seems like we just need to construct a SYK-like model where the scaling dimension of the fermion is actually not 1/4 but something different. Okay, so indeed we have such theories which is called SYK-Q model. It means that if we only have like a Q-body interaction, okay, if we only have a Q-body interaction, this kind of fermion interaction theory, then actually every fermion will have a scaling dimension 1/Q. Okay, so if a scaling dimension 1/Q, it will give us some different scaling of the electron current operator. And then it will give us different scaling of the resistivity and the conductivity. Okay, but actually the Q-body interaction will be pretty unlikely. I mean, pretty hard to imagine in the condensed matter system, okay? Because normally we only have a 4-body interaction, okay? So now our goal becomes actually, can we construct a 4-body interacting, non-random Hamiltonian with a tunable scaling dimension of the fermions, so we can use that model to construct a lattice model where the scaling of the transport can be tuned anywhere between 1 and 2, okay, in the lattice model. So that becomes our goal, okay? That becomes our goal. So, so indeed, we construct something like that, okay? So this is the model we start with, okay? So it's a 2-orbital model and still based on the 3 index tricks, okay? Based on the 3 index tricks. We have our psi fermion and the chi fermion, okay? And now you can see that because we use the 3 index trick, okay, so the interaction becomes non-random, okay? Interaction becomes non-random, okay? And then actually the Schwinger-Dyson equation becomes slightly more complicated because we have a 2-orbital fermion. So every one of them will have their own Green's function and self-energy, okay, self-energy. But actually you can see that this self-energy will come from contribution from psi and chi, and the self-energy of chi will come from contribution of psi and chi as well. Okay, so there's a mixed Schwinger-Dyson equation. Okay, there's a mixed Schwinger-Dyson equation. Question? Sorry? And oh, sorry. So the A, B, C, they sum over from 1 to something. And sorry, M is a square root of M1 times M2. Yeah, M1 times M2. Yeah. Right, okay, so this is the Schwinger-Dyson equation. So basically, the self-energy of psi is the Green's function of psi times the 2 Green's function of chi, okay, because actually you contract this fermion, actually you have like a one fermion line of psi and 2 fermion line of chi. The same thing is here. The self-energy of chi is a 1g chi times a 2g psi, okay? So this kind of self-consistent equation gives you a very strong constraint of your solution. So we follow the, and also we can introduce another parameter which is the filling factor, okay, which is the filling factor. So you can see that in this model, psi and chi, they are separately conserved, okay, they are separately conserved. So we can introduce like a filling factor for the psi fermion and also for the chi fermion. So we introduce like a q psi between 0 and 1 as the filling factor for the psi fermion, and also for the filling factor of our chi fermion, the q chi as well. Question?
To get those Schwinger-Dyson equations, you only drop terms suppressed by 1 over n, or also 1 over n?
Oh yeah, so we assume n and m both large at the same order. Yeah, so they're both large at the same order. Yeah, right. So it means a large n limit. But actually, we can take them to be the same as well. So if you want.
Do you need to fix the ratio between n and m?
Well, in this, yeah, at this stage of the story, yes. Actually, you need to make sure they scale the same way, to make sure that the same set of diagram will actually be dominant diagram in the Schwinger-Dyson equation. If they scale differently, I mean, you have to consider some other diagrams. Also, the whole counting will be different. Yeah, so we have to assume that n and m they scale the same way, although they may not be the same. They differ by an order 1 factor, for example. Yeah. Okay, so it's a slightly complicated coupled Schwinger-Dyson equation, and we choose the standard way of solving SYK kind of a model. We give an ansatz of the correlation function. This is the ansatz in the real time, imaginary time space. And this is the ansatz in the frequency space, and we assume that, we actually assume this frequency can be both real and imaginary. So there are several coefficients and factors which can be determined through the self-consistent equation. So it turns out that the self-consistency gives us 5 different equations, okay, give us 5 different equations, okay. They are complicated, but they're soluble, okay, the complicated are soluble. And there are 5 unknowns. Okay, there are 5 equations and 5 unknowns. This is the most important information. So what's our unknowns? So scaling dimension of the psi fermion, scaling dimension of the chi fermion, and some coefficient theta, and also some overall coefficient c psi and c chi. So it turns out that in the equation, only the c psi times c chi appears. So we can view c psi times c chi as a 1 unknown. Okay, so in total there are 5 unknowns: c psi times c chi, and 2 deltas and 2 theta. So there are 5 equations and 5 unknowns, so it's totally soluble. Okay, totally soluble. Okay, and most importantly is this equation. This equation is most important. Okay, So it means that it only, we only need to satisfy that the scaling dimension of the psi and the chi, the sum to be 1/2. Okay? So if psi and chi are the same fermion, then every one of them will have scaling dimension 1/4, then we're only going to get linearity resistivity. Okay? But now in this model, the constraint is the scaling dimension of them add up to be 1/2. Okay? And their scaling dimension can be, so their individual scaling dimension can be determined through other consistency conditions. Okay? So that's why we can get different scaling. Okay? Question?
So you're saying from Schrödinger equations at low energies, you can only determine the product of C.
Yeah, right. Maybe there's a
Use some UV input to
maybe. Yeah, that's a good question to ask Xiaochuan actually. So right.
I
Yeah.
have some similar experience as well.
Okay. Yeah. Right. Because right. I mean, yeah. I don't know how to determine them separately, but actually,
You
yeah.
need to basically connect with the UV.
Maybe. Yeah. Maybe. Right. Yeah. Anyway, so the most important message I'm trying to deliver is that this model, it requires the, so this model requires the scaling dimension of psi and chi add to be 1/2. So it means that actually each of them is tunable. Okay, each of them is tunable, and they are tunable through the filling factor. Okay, so actually, so these equations can be approximately solved perturbatively as a polynomial with the filling factor away from 1/2. Okay, if we have a half filling, then everything will be the same as the SYK model. But suppose the filling factor is away from 1/2, we can do perturbation, and we can show that we can write everything in terms of polynomial of this filling factor Q psi. So Q psi equals to the big Q minus 1/2. Okay, so it's a filling factor away from 1/2. So indeed, we can see that actually the scaling dimension of psi and chi, they depend on the filling. Okay, the filling actually will change the scaling dimension of psi and chi. Okay, will change the scaling dimension of psi and chi, and they always add up to be 1/2. The sum of them is always 1/2. Okay. Okay, so now we can just so now we build the cluster model as we always do. Okay, we actually define different clusters, and every cluster is my model. And then we turn on tunneling between different clusters. We turn on tunneling between different clusters. And this tunneling will give us a current operator, which is again a fermion bilinear operator. And then we calculate the correlation function between the current correlation. Okay? And then we get some complicated function. Okay? We get some complicated function. Complicated. But actually, eventually, we can just schematically write the DC conductivity like this. Okay? DC conductivity like this. So delta is the scaling dimension of the one of the two fermions. Okay, scaling dimension of one of the two fermions. Okay, so now you can see that actually this alpha. Okay, if I just reverse it, take an inverse of this, this alpha can be tuned by the filling factor. Okay, so it can be tuned anywhere between 1 and 2. Okay, indeed, it can be tuned anywhere between 1 and 2, depending on the filling factor. Okay, depending on the filling factor. Okay, so this is the first model, and then the second model we tried is also, similar, but actually it has a different symmetry. So actually we have like this kind of model. This kind of model actually we can see that we still have two orbital model. So still it has the desirable feature that the sum of the scaling dimension of these two fermions will be 1/2. But now we don't have a U1 charge conservation of each of them separately, but we only have a total fermion number conservation, but the solution is actually similar. Okay, the solution is similar. Still, we can actually define a cluster model based on this one, every cluster, and connect them using hopping, and then we can follow the same calculation. And then you can see that this is the scaling. The transport scaling power alpha. Depending on the this is the filling. Okay, this is the filling factor, and also M2 over M1. M2 and M1 is just this index actually take a different range. Okay, from 1 to M1, the other from 1 to M2. Okay, okay. So there's another another mutant of this model which I'd like to mention is that actually we can actually try to view some of the index as the lattice coordinate. Okay, as a lattice coordinate. So for example, the previous model I wrote down can be rewritten like this. Okay, can be rewritten like this. So this is the model defined on the square lattice. Okay, this is the model defined on the square lattice. Okay, and as I said before, there are 3 index for every fermion. But now, every fermion will carry 3 index. One is a spin. The other 2 is a spatial coordinate. Okay, the other 2 is a spatial coordinate. So I basically at the n, the n parameter in my model becomes the range of the interaction. Okay, becomes the range of the interaction, and m1 and m2 becomes the spin index of my interaction. Okay, so it turns out that if I take n equals to 3 and m1 and m2 equals to 2, this model takes a very simple form. Okay, this model looks like this. It's just a Haber interaction plus Heisenberg plus a next neighbor repulsive and also a ring change. Okay, ring change means I take these 2 fermion and hop to these 2 fermion. Okay, on a small placket. Okay, on a small placket. Okay. Okay, so yeah. So this model in the large n limit, but actually large n and large m limit actually will be sort of an unphysical limit because we need a long-range interaction. But actually finite n, finite m actually will be a local interaction. Okay, but then actually we can see that within a temperature range, actually we are still supposed to expect rho to the power alpha, and alpha is equals to 1 when I take m1 equals to m2, but alpha can be tuned anywhere between 1 and 2 if I change the particle density. Okay, if I change the particle density. So actually this scaling is supposed to hold within a finite energy window. Okay, for finite n and m, this scaling is supposed to hold within a finite energy window. So it turns out actually in Subir and collaborators' earlier paper for the SYK model, they showed that actually SYK scaling, even with finite n, the SYK scaling can hold within a finite energy window between the SYK interaction and an exponentially suppressed energy scale. So actually there could be a very large energy window where a temperature window where the linear T scaling actually holds. So the same story may carry over here, but actually we need to do the 1 of n and 1 of m analysis for this set of a model. But actually, my understanding is that so far for the 3-index tensor model, the 1 of n, 1 of m analysis is not available yet, because for the 3-index tensor model we don't have a G sigma kind of action to do the 1 of n calculation. But actually, the hope is that for this kind of model, at least even for finite n, finite m, there should be we expect there should be a finite energy window where this kind of a non-fermionic scaling based on the SYK type of physics still hold. Okay, within a large enough energy window. Okay, so I'm out of time, but this is also my last slide. Okay, so in summary, so actually we construct, based on SYK physics, not exactly the SYK model, we construct non-fermionic liquid state with the transport scaling alpha can be tuned between 1 and 2, and it can be tuned by the charge density. Okay, but it's, as was pointed out before, one awkward feature is that the coefficient of this resistivity is not going to be order 1, so it's not going to be a Planckian medal. Okay, so there's many interesting questions to explore. Like actually, the Planckian kind of a medal was actually explored using the SYK physics in the momentum space. Okay, by Subir and a collaborator. Okay, earlier this year. And also another interesting question, which actually I haven't figured out, is can we actually have a SYK kind of a model in the momentum space? But actually, can we actually construct a Fermi arc? Okay, can we actually construct? So it means that on the Fermi surface, part of the Fermi surface actually may have a SYK kind of a physics, so it doesn't have a quasi-particle pole. But on the other part of Fermi surface, maybe it's a more Fermi-liquid-like. Okay, it could be Fermi. But actually, this is something I'm still thinking about. I don't have a model yet. Okay. So with that, I'd like to conclude my talk. Thank you for your attention.